Today we're going to talk about covalent bonding, which is a type of bonding that functions in a different way than ionic bonding and works for substances where ionic bonding doesn't make any sense. In covalent bonding, what holds the atoms together is not an attraction that they have for each other, like in ionic bonding. In ionic bonding, you have a positively charged ion, like a sodium, for example, or a negatively charged ion, and the positive and the negative have a mutual attraction for each other, and so they stick together in a crystal. In covalent bonding, what holds the two atoms together is the mutual attraction that they have not for each other, but for a shared pair of electrons. This will only happen, just like in ionic bonding, if the bonded situation is energetically favorable to the unbonded situation. So if the resulting bond has less energy stored in it than the individual atoms, well, then a bond will form. Otherwise, it won't. G. N. Lewis, the same person who gave us Lewis dot notation, or Lewis symbols, also gave us a way of modeling how molecular or covalently bonded structures hold together. In Lewis structures, covalent bonds are shown by lines. So a shared pair of electrons is typically a line. Some people do use pairs of dots, but I don't think that's a good idea because you want to distinguish between electrons that are shared by atoms and electrons that are locally attached to a single atom. Unshared electron pairs that belong to an individual atom that's part of the molecule are pairs of dots, like in Lewis dot notation. The number of electrons that are in the structure when you're done drawing this sort of a picture is what a Lewis structure is equal to the sum of all the valence electrons that were in the atoms. So here's how you draw Lewis structures. The first step is use the dot symbols for all the atoms that are going to be in your structure and count all the valence electrons that are present. So for example, if I were doing NH3, nitrogen has got 5 dots because it's a column 5, and the hydrogens have 1 dot because they're column 1 and there's 3 of them. So I'd add this all up, and 5 plus 3 makes 8. So I'd know that I had 8 valence electrons to work with in my structure. The next thing to do is connect the atoms in a skeleton structure. Now there are some hints that we can use for skeleton structures to get them correct. One is this. In oxyacids, you're always going to have a chain that's H connected to an O connected to another nonmetal. So here's an oxyacid, H2SO4. I know that somewhere in that structure I'm going to have an HOS chain, at least one. Another hint is the farther from the edge of a periodic table the element is, the farther it's probably going to be from the edge of the molecule, most of the time. So things closer to the middle of the table are usually closer to the middle of the molecule. Another hint, hydrogen has to be on the outside of the molecule. Remember, hydrogen can only make one bond, and so you can't have this. You can't have hydrogen bonded to two things, so it's got to be on the outside. And then there are some bond preferences that we can see from the number of unpaired electrons that exist in each of these elements. Things that are in group 4, like carbon, for example, have 4 unpaired electrons, one on each side of the little square that you imagine when you're drawing Lewis dot notation. Well, because carbon wants a full 8, that means there are 4 places where it is likely to share an electron with something else. And so carbon and other group 4s are typically going to make 4 bonds. Nitrogen is a group 5. All group 5s have 5 dots, but the way this dot notation is drawn, that means there are 3 spots where there are unpaired electrons. And those unpaired electrons are likely to be shared with an unpaired electron from something else, and so you'll have 3 bonds typically with group 5s. Group 6s, like oxygen, end up having 2 unpaired electrons, so 2 places where sharing is likely to occur, and so we end up often seeing oxygen and sulfur and selenium, everything in group 6, making 2 bonds. And group 7s, like fluorine, have got 7 dots, which means 3 pairs and 1 unpaired electron. And so halogens, like fluorine, chlorine, bromine, iodine, are typically going to make 1 bond. Now, these aren't hard and fast rules, but they're often followed when you have the chance. Another hint is that compact arrangements are usually more accurate than long, stringy things. So if I had SO4, I had to make a skeleton for that, I would probably be better off if I made it like this than if I made it like this. And built into this is another little hint. If you have a binary compound, something that's made of only 2 elements, typically in the skeleton, you want to put the first thing listed in the middle and then the second thing listed around the outside. It doesn't always work that way, but very commonly it does. Then once you have a skeleton structure made, you want to fill up the octets. You want to make sure that everything has a full octet so that it's stable. There are 3 notable exceptions that you'll run across. One of them, of course, is hydrogen. Hydrogen only needs a duet, and so hydrogen is going to make its one bond, and that's it. Beryllium will have a quartet. Beryllium is going to make 2 bonds, one on each side, and that will satisfy. That's stable for beryllium because lithium is closest noble gas, and it's just too small of a nucleus to support any more than 4 electrons. And another exception is boron. Boron will have a full sextet, so that's 6 electrons, and they'll come in 3 shared pairs. So boron will make 3 bonds, and that'll be stable. If after you're done filling the octets, you find out that the structure has too many electrons, what you want to do is form multiple bonds. Let's look at an example. An example would be CO2. If I make an electron count, carbon is column 4, so the 4 dots, and oxygen is a column 6, so it's got 6 dots, 6 valence electrons, but there's 2 of them. So all told, that's 12 plus 4. That's going to give me 16 electrons that I have to have in my structure, no more. When I make a skeleton, it makes sense to put carbon in the middle because it's closer to the middle of the table, and put the 2 oxygens on the outside. Now I have to fill octets. Oxygen has 1 bond, that's 2 electrons. It needs 6 more to have a full 8. So on the remaining 3 sides of the oxygen atom, I'll put a pair each to get my 6 electrons. Carbon's making 2 bonds, that's 4 electrons. It needs 4 more. So I'll put 2 more pairs on the remaining 2 sides of the carbon. Now, this is stable because oxygen and carbon both have 8 electrons, a full octet. But if I do my electron count, it's not right. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, which is too many electrons. So if this happens, what you want to do is erase a pair from each of 2 adjacent atoms. So in other words, atoms that are bonded to each other, and then put another bond in between so you can maintain stability. So now this oxygen still has a full octet, 2 here, 4, 6, 8, and so does this carbon, 2, 4, 6, 8. Still stable, but now the electron count has been diminished. And so this is more like what nature is going to actually do. The count is still too high, 2, 4, 6, 8, 10, 12, 14, 16, 18. So in that case, we can just do it again. And now the count is correct, and everything's stable. What else happened is we noticed that carbon is now making 4 bonds, which is its bond preference, and the oxygens are both making 2 bonds, which are their bond preference. Now, if a structure has too few electrons, you want to put electrons in on the central atom, and we'll see an example of when that happens later on. And they're always going to be in pairs. Electrons in this class are always going to come in pairs. Let's do some examples. HClO3. We'll make our count. You don't actually have to draw the dot notations. You just look at the columns. So column 1, there's 1 electron. Column 7 gives me 7 electrons. Column 6 is where oxygen is. That's 6 electrons, but there's 3 of them. So 6 times 3 is 18. So this is going to give me a total of 26 electrons in my structure. Skeleton structure. Well, which is closer to the edge of the periodic table, chlorine or oxygen? It's a tough call. They're both 1 step in, basically, from the edge. However, I noticed that this is an oxyacid. It starts with H and has oxygen in it. So I want to make sure that I have an HOCl chain in here. Now, because chlorine is the first thing listed here, compared with oxygen, I'm going to put that in the middle and surround the chlorine with oxygens like this. So there's a skeleton that makes some sense to me. It's not stable. I have to fill octets. So oxygen needs 4 more. This oxygen up here needs 6 more. And so does this oxygen. Chlorine's making 3 bonds. That's 6 electrons. It needs 2 more for a full octet. Now, I'll count my number of electrons and make sure that it's 26. On this oxygen, I've got 6 in lone pairs. 6 here, that's 12. 2 from chlorine makes 14. 16 and 18 come from the oxygen, lone pairs. And then I'll count up the electrons in the bonds. 20, 22, 24, 26. So this structure is correct. Give this one a try. stop the video and try and draw a Lewis structure following the rules, and then I'll give you an answer in a minute. Well, carbon's column 4, so that would give me 4 electrons. Oxygen's a column 6, that would give me 6 electrons. So a total of 10 electrons should be in my structure. Skeleton is real easy here because you only have 2 atoms, so you stick them to each other. Then fill octets. Each one of these things needs 6 more electrons, so that's what I'll do. And count. Well, I've got 6 in lone pairs on both the carbon and the oxygen, so that's 12, plus the bond makes 14, so obviously I have far too many electrons. I'll take a pair away and replace with a bond. That reduces my count by 2. Now I've got 12 electrons in my structure. So, still too many. I'll do it again. Now I have a triple bond, and my electron count is correct. Also, you'll notice everything's stable. Try this one. Sulfur and oxygen are both from column 6. So that's 4 times 6 total, or 24 electrons in the structure. I'll put sulfur in the middle, surrounded by O's. That's the skeleton that makes sense to me. And then fill octets. Sulfur needs a pair. Each of the oxygens needs 3 pairs. Now I've got stability. If I do my electron count, I've got 6 in lone pairs on each oxygen. So in 3 places, that adds up to 18. Lone pair on sulfur makes 20, and then the bonds make 22, 24, and 26. So I have too many electrons. So I'll pick any of my oxygens, it doesn't really matter which one, and the sulfur, and I'll make a double bond. Now my electron count is proper, and everything has a full octet. Try this one, SF4. Okay, sulfur, column 6, so that's 6 electrons. Fluorine is a column 7, and there's 4 of them. 7 times 4 is 28. So 6 plus 28 gives me the total number of electrons that should be in my structure, and that's 34 electrons. I'll put sulfur in the middle. Halogens prefer to make 1 bond anyway, so I'll put those on the outside, and then fill octets. Sulfur has a full octet, so it's good, but fluorine doesn't. Each of the fluorines need 6 more electrons, 3 pairs. Remember, always think about a square around these things when you're filling octets, and every side of the square should have either a bond or a pair of dots. Now I'll make my count. Each fluorine's got 6 in lone pairs, and there's 4 of them, so that makes 24. With the bonds, it's 26, 28, 30, 32. Well, that's not enough, because I'm supposed to have 34 electrons. So this is a case where I have too few electrons in my structure. And I solved that problem by putting the extra electrons, the extra 2 in this case, on the central atom in pairs. It's okay for sulfur to have an expanded octet, to have more than a full 8. And the reason for that is because sulfur is in period 3. And that means its principal quantum number is 3. And that means it's got an S and a D and a P sublevel. And so period 2s can only have 8 electrons. S2, P6. But a period 3 has that D sublevel that can absorb more electrons, and so an expanded octet, this is called, is possible for things that are in period 3 and lower. For polyatomic ions, you do everything the same as for doing molecules, except for you add electrons to equal the negative charge that's on your ion, and you subtract electrons to make up for the positive charge that's on a cation. So here's an example, ammonium. To draw a Lewis structure for this, I start out the way I normally would and just make an electron count. Nitrogen's in column 5, so that's 5 electrons. Hydrogen's in column 1, that's 1 electron, but there's 4 of them, so 5 plus 4 gives me 9 electrons. However, this is a plus 1 charged species, so that means there's a missing electron. So because of that, I will subtract 1 electron from my count, which leaves me with 8 electrons that should be in my structure. Skeleton's pretty easy because hydrogens have to be on the outside, so I'll put the nitrogen in the middle. Octets are full, hydrogens don't get any dots, and the nitrogen already has 8 electrons. And those 8 electrons are our count, so there's my structure. Now, when I finish off a polyatomic ion, I put square brackets around it, and then I install the charge up here. That's a little finishing touch for polyatomic ions. Here's another example. This is nitrate. Nitrogen's column 5, so there's 5 electrons. 3 column 6s will give me 18 electrons. So with the nitrogen and oxygen, I have 23 electrons. But this is a 1 minus charge species, so that means there's an extra electron in there. So I'll add 1 electron to the count to give me a total of 24 electrons. Now I'll make my skeleton, put nitrogen in the middle, surround it with oxygens, and fill octets. Each oxygen gets 3 pairs, and the nitrogen has 3 bonds, so it's going to need 1 pair for a full octet. Now I'll do my count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Now there are too many electrons in this structure, so I'll pick one of the oxygens, it doesn't really matter which one, and the nitrogen, and I'll make another bond. That gets my electron count to where it should be, and it makes this thing stable. Square brackets are the last thing I do, and install my charge up there. Sometimes it's possible to draw more than one valid structure that works out for a Lewis structure for the same compound. In those cases, we need some way to decide which is most likely the actual molecule that nature creates when the compound forms. One of the tools we can use to do this is called formal charge. Formal charge is calculated by starting out with the number of valence electrons in the unbonded atom. So like for oxygen or something in column 6, that would be 6. Then you subtract from that the number of bonds that are made to that atom. So if it's a double bonded oxygen, you would subtract 2 for the 2 bonds. And then subtract also the number of unshared electrons around the atom. So let's say we had a double bonded oxygen. This would have to have, if it had a full octet, 2 lone pairs. Here's how we would find the formal charge on this species. 6 electrons to start with, because that's the number of valence electrons in the unbonded atom, minus the number of bonds that are made to the atom. Well, that's 2, 1 there, 1 there, plus the number of unshared electrons. Well, we have 2 there and we have 2 there, so 4. So this is 6 minus 6, so this has a formal charge of 0. This allows us to choose between 2 valid Lewis structures to find out which one is the more accurate of the 2. The sum of all the formal charges will be equal to the charge on the species. So when you add up all the formal charges on a molecule like H2SO4, you should come up with 0. Let's draw a Lewis structure for H2SO4 and calculate the formal charges on it. So hydrogen, 1 electron each, that gives us 2 total. Sulfur, column 6, that gives us 6. Oxygen is also column 6, and there's 4 of them, so that's 24. 24 and 6 is 30, plus 2 gives us 32 electrons in our structure. A reasonable structure, this is a oxy acid, and so we're going to have an HOS chain. We'll actually have 2 of them to keep this symmetrical, and then we'll attach the other 2 O's to the central sulfur. Now, filling octets, I find that I need a lot of dots on O's, but sulfur already has a full octet with the 4 bonds. Now if I count, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons. So this is a valid Lewis structure. Now let's find the formal charges. For hydrogen, so 1 valence electron is unbonded, minus 1 bond gives us a formal charge of 0. So a single bonded oxygen is going to be 0. That means this other one over here is also going to have a formal charge of 0. Let's look at this oxygen here. Starting from 6, we take away 1 for the bond, and 1, 2, 3, 4, 5, 6 for the unshared electrons. So 6 minus 7 is negative 1. So a single bonded oxygen has a formal charge of minus 1. So this other single bonded oxygen will be the same. Double bonded oxygen, we have 2 of those here. Starting from 6, we take away 2 for the bonds and 4 for the unshared electrons. So that comes out to 0. The other double bonded oxygen will also have a 0 formal charge. Now let's look at the sulfur in the middle. This is column 6. Take away 4 for the bonds and 0 because there are no lone pairs. 6 minus 4 is positive 2. So the formal charge on the sulfur in this structure is plus 2. Now it turns out that the more accurate structure is the one that has the smallest formal charges. So it would be possible, but it doesn't seem like it'd be likely at first, to draw this a different way that had lower formal charges. I'm going to reproduce this in part without the full octets. I could give a lower formal charge on oxygen if I double bonded it. So instead of having 6 unshared electrons and 1 bond like I have in this structure here, I could have 4 unshared electrons and 2 bonds and still have full octets. If I did that for the other single bonded oxygen here, that's also legal. Sulfur can have an expanded octet because it's in period 3. If I keep these oxygens the way they were because they already had formal charges of 0, now let's look at what happens with sulfur. Double bonded oxygens, remember, are 0. So formal charge 0, 0, 0 for the hydrogens, and 0 for that other oxygen. Now for sulfur, 6 minus, now how many bonds are on sulfur now? 1, 2, 3, 4, 5, 6, and still no lone electrons. So now we have a formal charge of 0 on sulfur. Even though our Lewis structure drawing rules point us to that structure, this one is valid, and it's actually a better structure because the formal charges are lower. By lower, we don't mean more negative. We mean closer to 0. So if you can eliminate plus or minus formal charges and get them down to zeros, that's a better structure. So just to review, the sum of all the formal charges equals the actual charge on the species. And if you have 2 structures, the one with the smallest formal charges is the preferred structure. Let's take a look at these 3 Lewis structures for HNO3, nitric acid. Which one is the preferred structure of these 3? Take a look at it for a bit, and I'll give you an answer in a minute. Well, right off the bat, we know that structure number 3 is out of the question because the nitrogen here has an expanded octet. Nitrogen's in period 2, and they can't do that. So that's not even a legal structure. Now let's look at the other ones, and we'll make our decision by assigning formal charge. This O is a double bonded O. So 6, 5, 4, 3, 2, 1, 0. It's the quick way to get formal charge. Just count down from the valence electrons in the unbonded atom. Single bonded O, 6, 5, 4, 3, 2, 1, 0, minus 1. I think we saw that before. Single bonded oxygen is minus 1. Nitrogen, starting from 5, 4, 3, 2, plus 1. Double bonded oxygen, those are zeros. And the single bonded hydrogens, 0 as well. Let's check out structure number 1. For this oxygen, it's a single bonded oxygen. We've already seen those are minus 1. And same thing down here. Let's look at the nitrogen. Starting from 5, 4, 3, 2, plus 1. Oxygen, starting from 6, 5, 4, 3, 2, 1, plus 1. So out of these 3 structures, the one that's preferred is the one that has the lowest formal charges. Well, I've got minus 1s in 2 places in structure number 1, and plus 1s in 2 places in structure number 1. Structure number 2 has a plus 1 and a minus 1. So overall, structure number 2 is a preferred structure. Find the best structure for POCl3. So here's what I want you to do. Stop the video, draw a Lewis structure, just draw the first Lewis structure that makes sense to you, and then see if you can improve on it and get the formal charges to be lower. I'll come back and give you an answer in a bit. Well, phosphorus is column 5, so that gives me 5 electrons. Oxygen's column 6, there's 6 more. And then 3 7s for the chlorine gives us 21. So when you add this all up, you get 32 electrons in your structure. Phosphorus is closest to the middle of the table, so I'll put that in the middle, and I'll surround it by 3 Cl's and an O. And then I'll fill octets. 3 pairs on chlorine in 3 places, and 3 pairs on oxygen. Now everything's stable, it's got a full octet. I'll count to make sure I have 32. So in lone pairs I have 6 per atom, per outside atom, and that's 24 total. Then with the bonds it's 26, 28, 30, 32. So this structure is okay. Now let's do formal charges. For chlorine, starting at 7, I'm counting down to 6, 5, 4, 3, 2, 1, 0. So a single bonded chlorine is a 0. So this single bonded chlorine will also be 0, and so will this one. Oxygen. We've done single bonded oxygen before. Counting down, 6, 5, 4, 3, 2, 1, 0, minus 1 is the formal charge. Phosphorus is column 5. So counting down from 5 with the bonds, 4, 3, 2, plus 1. So there are the formal charges on that structure. If you look at this structure, you realize that phosphorus needs to have one more bond or one lone electron to get down to 0. And oxygen needs to have one less electron or 2 less electrons in a bond to get down to 0. So we could accomplish that by taking this phosphorus and double bonding it to the oxygen. So this is a better structure with lower formal charges. Single bonded chlorines are each 0. A double bonded oxygen is going to be 0. And then counting down from 5 for phosphorus, we go 4, 3, 2, 1, 0. So this structure has all zeros for formal charge. That's the better structure. And it's allowable because phosphorus is in period 3, and period 3 and lower on the periodic table can have expanded octets. There's another phenomenon that happens when you draw Lewis structures that gives us some insight into how molecules actually behave. And we can see this with this polyatomic ion, NO3 1-. The concept is called resonance. I can draw this Lewis structure by first of all counting up my electrons. I have 5 plus 18 plus another 1 for the negative charge, and this gives me 24 electrons total. Now when I draw the Lewis structure, I end up with N bonded to O's in 3 spots, and when I fill octets, I will end up having too many electrons. If I count 6 in lone pairs in 3 places on the O's gives me 18. The lone pair on nitrogen gives me 20, and then the bonds gives me 22, 24, 26 electrons, which is too many. So I'm going to need to make a double bond. Where do I make it? Well, I could do it 3 different ways. I could do this, double bond to the one on the right. I could do this, double bond to the one on top, single bond to the other 2, or I could do this, double bond to the one on the right and single bond to the other 2. And this should have square brackets on it and charge. So which one is right? Well, it turns out that they're all equally valid. If you were to check formal charges, you'd find that they were all the same. So you can't really distinguish between the 3 of them. And in fact, you don't have to. All of them are equally valid structures, and really none of them is right. That double bond, that second bond between the O, is really in all 3 positions. This is a concept known as resonance. And in the double bond, what it's doing is it's switching positions. It's constantly forming and reforming in different oxygens around the structure. So we say that the multiple bond is equally distributed among the 3 different positions. And structures that exhibit resonance like this one are actually more stable than the individual structures would indicate. And so none of them is right, but in fact, it's oscillating back and forth between these 3 different conformations. Another way of drawing this would be to show dotted lines that show a sort of a partial bond, not exactly double, between the N and all 3 O's. That's actually a little bit more accurate. Another famous species that does resonance is benzene. Very stable structure. Sometimes that's good, sometimes that's bad when it's in a part of pollution. You can see that the positions of the double bonds are switching from the first, third, and fifth carbon to second, fourth, and sixth carbon. Well, in fact, they're switching back and forth continuously, and you have resonance between these two species. And so organic chemists will often write that structure this way and just put a ring in the middle to show that delocalized resonating bond.